Welcome back. This video is part 2 of our discussion of section 4.1. In the first video we looked at scatter diagrams, and in this video we're going to move forward with talking about something called a linear correlation coefficient. So our objectives here in this video, we're going to describe the properties of the linear correlation coefficient, and then we'll move on to computing and interpreting the correlation coefficient. But now, before we talk about its properties, let's look at a couple examples of types of relationships that we can typically see when we have bivariate data. So remember that with bivariate data we're talking about having an x variable and a y variable. We'll sometimes call that the explanatory and the response variable. And the relationship that we're going to be principally interested in this chapter is shown here in graphs A and B. And it's what's called a linear relationship. And you get a linear relationship when, as your x variable changes, and let's say as x increases, the values in the y variable tend to increase at a relatively constant rate. So as x increases, we've got our values of y. They tend to increase at a relatively constant rate. And if you think about this scatter of points, it lies in roughly a straight line pattern. And so we call this a linear relationship. And we see the same thing over here in graph B. As x increases, y tends to decrease in a roughly straight line linear pattern. So these two graphs are examples of what we call a linear association between variables x and y. And the other example that we should think about here is shown down here in graph E. What's happening here is, as x increases, our values of y tend to stay roughly the same. They bounce around a little bit, but they're not systematically increasing or decreasing. And so what's going on here, we call this no relation. So there's no relation between x and y. As x increases, the y value tends to remain roughly the same. So let's look at another example. Here we've got an example of a scatter plot of 10 or 11 individuals where we've measured both their years of education and their income. So each of these points on the plot represents a different individual. We've plotted their years of education down here along the x-axis. We've plotted their income along the y-axis. And it shouldn't be a surprise that as we see for these individuals, as their years of education increase, their income tends to increase as well. And we could look at this pattern and say, well, there appears to be evidence of a linear association between these two variables, years of education and income. As years of education increases, income tends to increase, and it does so in roughly a straight line manner. And here's another example. Again, we've got about 10 individuals, 10 students in this case, and on these students we're measuring their typical number of hours per week they watch television, and plotting that value along the x-axis, and plotting their GPA along the y-axis. So what we're seeing here is we've got several students who reportedly watch 4 or 5 hours a week of television, all the way up 10, 15, 20, 25 hours a week of television. And what we can say again is there appears to be something like a straight line relationship here between hours per week watching television and GPA. As hours per week watching television increases, GPA tends to decrease, and it does so in roughly a straight line manner. And so now here's a key idea. Scatter plots like this are very useful for examining the data and looking at what type of relationship may exist between the variables. However, what we need is something a little more quantitative. We need a numerical measure of the relationship between these variables. And so that's going to take us to what we'll call the linear correlation coefficient. Sometimes you'll see textbooks will call this the Pearson product moment correlation coefficient. It's usually given by the symbol little r. And as you see, there's a rather complicated looking formula for calculating this. Now, we won't ask you to calculate this formula by hand or using your calculator. We'll simply use software to calculate it. But it is worth taking just a minute to look at the formula to get some idea of what's going on here. What you can notice here is that our formula for R, the formula for the correlation coefficient, is a function of the x's and y's. It's a rather messy, complicated looking function, but remember we're talking about having bivariate data, so we have two variables measured on each individual, an x and a y, and the formula for R is simply this messy looking function of the x's and y's. So I've got the x's in here, I've got x bar, well that's the sample mean of the x's. I've got s sub x, that's going to be the sample standard deviation of the x's. I've got y sub I, and I've got y bar, and s sub y, that's the sample mean and the sample standard deviation of the y's. And we take this expression in the numerator and divide by n minus 1. Well, remember that n is simply the sample size. So what we've really got here is a statistic. R is a value calculated as a function of our sample data. But as I said, we're not going to worry about calculating this by hand. We'll let the software do it. But it's important to just think about the fact that whatever our value for R is, it's simply calculated directly out of the data. Now, it's not obvious from looking at this formula, but there's a clear set of possible values that R can attain. It turns out that R is always going to be a number that runs somewhere between -1 and +1. So the smallest possible number would be -1.0. The largest possible number for R would be 1.0. And in fact, -1 and +1 are sort of unusual cases. Normally R is going to be a value somewhere in between. Now what we'll say is, if R is close to -1, then that indicates evidence of a negative linear relationship. And we'll talk in a second about what that means to talk about a negative linear relationship. If R is close to +1, that's evidence of a positive linear relationship. And if R is close to 0, that indicates little or no evidence of a linear relationship. So in a sense, there's two pieces of information here. We're going to have the sign of R, positive or negative, and we're going to have its absolute value, how far away it is from 0. And now if you remember our definition of R, we said that R measures the direction and the strength of the linear relationship between two variables. Well, the direction and the strength are given by the sign of R, if it's positive or negative, and its magnitude, how far away it is from 0. So let's go back to our example about years of education and income. We said that there appears to be a linear relationship between these two variables, that it appears to be a positive linear relationship. And by positive, we mean that as the x variable increases, the value of y tends to increase as well. So we'd say that years of education and income have a positive linear relationship. And if we look at our other example, hours per week these students are watching television versus their GPA, again we said there appears to be a linear relationship between these variables. As hours increases, GPA tends to decrease in roughly a straight line manner. But we can go further now and say that it appears to have a negative linear relationship between these two variables. And by negative, what we mean is as the x variable increases, the y variable tends to decrease. So x and y have a negative linear relationship. So now we can take this a step further and go ahead and calculate the Pearson linear correlation coefficient for these two variables. And since it looks like there's a negative linear relationship between hours per week of television and GPA, we'd expect R to be negative. And in fact, it turns out, if we calculate the correlation coefficient for these two variables, we get an R of negative 0.813. That's a fairly strong negative correlation. Remember that correlations can be as small as -1 and as large as +1. Well, here our correlation coefficient is negative 0.813. That's pretty strongly negative.